Right. Brilliant. Right. We are gonna start chapter 2, but for those who missed chapter 1 has been an introductory section. Nothing has been there. We introduced some concepts, our objectives. Please go through it. With some concepts, we have introduced them. That is terminologies like mechanics, statics, dynamics, fluid mechanics, fluid dynamics, aerodynamics, hydrodynamics, gas dynamics, metrology, oceanography, and hydrology. We talked about them. We defined the fluid in a similar way. We define a solid. We introduce shear stress and strain as well. And we went further to explain further about these strains and stresses, right? We went and defined fluids in terms of their intermolecular connections, the forces between intermolecular forces. And we said solids more organized because there is a very strong intermolecular forces. In liquid, slightly looser. In gases, very loose intermolecular forces. We went and looked at studying fluid mechanics from a large scale to smaller scale. We went into applications of fluid mechanics, and there are many applications, as you can see. We introduced the no-slip condition, and we said this is a very important point in fluid mechanics. Close to the wall, the velocity of all those molecules or atoms attached to the wall is zero, and therefore something called boundary layer develops close to the wall. We talked about a brief history of fluid mechanics, and we introduced Reynolds number, right? We talked about classification of fluid mechanics, and we said it classified basically either on property or a geometry. We started with viscous inviscid flows, and that based on the friction and viscosity close to the surface. External and internal flows, compressible and incompressible flows, laminar and turbulent flows, natural and forced flows, steady and unsteady flows, one-dimensional, two-dimensional, three-dimensional flows. And we took this example. We went to thermodynamic systems, and we talked about open systems and closed systems, and what is the difference between open and closed systems. We went to units and dimensions, and we explained the difference between units and dimensions, right? سكر المايك يا ابني، سكر المايك. أياد. Hello, do you hear me, guys?
Yes, doctor.
Yes, doctor.
Right. Okay, brilliant. We talked about SI units and British units, right? And we talked about energy and its units, right? And we talked about something very important, unit conversion and homogeneity, dimensional homogeneity. We said an equation, if you have an equation, all the added terms should have the same units. In other words, you cannot add pressure plus mass plus energy and say it is equal to zero. That is not possible. Mass plus mass plus mass equal mass. Energy plus energy plus energy equal energy. Potential energy plus kinetic energy plus internal energy equal to energy, right? So that is what we need. What we mean by what? Dimensional homogeneity. So we went into what? Some examples to differentiate between units. And we talked about mathematical modeling of engineering problems, and we said there are specific steps. If you have a problem, if you have a fluid problem and you want to analyze it and come out with an output, that's to say a solution, there are specific steps. You have to follow them, and we said these steps are very important when you come to writing your final year project. Okay, we talked about simple models, complex models. These are the steps, how to solve them. and how to reason. If you develop a mathematical model to a specific fluid problem and you came out with a result, you have to apply reasoning, because mathematics should not go against reasoning, right? And we said this is not reasonable results here. To those who have been pressing with us, engineering softwares, we talked about ANSYS fluid mechanics, which is available for you guys in your labs. Please try to look at it carefully. Accuracy and precision, we talked about it as well. And we said it is very essential to take as much digits as possible in order to get the right answer. That is chapter 1. Okay? To those who did not attend, I'm not going to go through it again. Chapter 1 is gone for good. Okay? We will start chapter 2 and we will finish it next Thursday during the 2-lecture period, but let us start it. Chapter 2 talks about what, guys? Properties of fluids. The title is very clear. We are going to explore and focus on properties of fluids. That is what is chapter 2 about, which is still an introductory chapter, in my opinion. You did not go into fluid mechanics yet. You are still talking about concepts, main concepts. If you look at the slide 2, it tells you, you show that there is a pen, right? Something like a pen, and there is a drop hanging on the pen. We know that everything against gravity should be pulled by gravity, ya shabab. صح? Am I right or wrong?
Yes, doctor.
Yes.
Yeah. So here, the thing that intrigues us, the thing that should raise your attention is why this drop is sticking to the head of the pen. Why is it not falling down? There must be a collective of properties, a collection of properties that actually work together in order to make this droplet, although it is heavy, but it still stick to the pen. And that is what is the subject is about. What is this chapter about? So our main objectives, main learning outcomes, the main points that will be examined: have a working knowledge of basic properties of fluids. We would like to develop our knowledge of properties and understand continuum approximation. Continuum, underline it, we will talk about it. Have a working knowledge of viscosity. Viscosity, gentlemen, actually, most of the science of fluid mechanics is mainly associated with one single property, viscosity. So what is viscosity and the consequences of the frictional effect it causes in fluid flow? And then we will come to see some applications of these properties, which is calculation of what? Capillary rise and surface tension. So these are application of the properties. These are the 3 main points that we are looking forward to achieve behind this chapter. Now, as an introduction, we'll talk about properties, guys. I know you guys knows a lot of properties of fluid flows or fluid in general. Talk about the mass, talk about the volume, talk about the temperature, talk about the pressure, talk about the density. These properties, I think you know them so far. So far, you know them very well. So we call them, these are properties of a fluid. Although, by the way, the mass and the volume, in my opinion, they are not properties. But the temperature, the density, and the pressure is properties. Because usually, gentlemen, a property change with conditions, right? The mass and the volume is something like scalars, right? Now, there is something very important. We divide properties into intensive and extensive properties mainly. So what is the difference between intensive and extensive, guys? One of them depends on the volume and the mass. One of them is not dependent. Like, for example, look at Look at this box and look at this box. This is the whole box, and then we divided the box into two. Which property has been affected, gentlemen?
The mass and the volume.
The mass and the volume are affected. These are extensive properties. But the temperature, pressure, density will not be affected if you divide into two or if you divide into 1,000. And these are called what, guys? Intensive properties. Now, when we divide, for example, the volume V by the mass M, we get what, guys? We get meter cube by what, guys? By kilogram. صح? Am I right or wrong?
Yes, right, Doctor.
Yes.
Divide the volume meter cube by the mass kilogram. That is meter cube per kilogram. Whenever you divide by the mass, you get something called a specific property. Do you know what is the difference between intensive, extensive, and specific property? Let us come to the phenomenon of continuum. The phenomenon of continuum is very important, gentlemen, in order to what? To analyze, and in reality, not only fluid system, any system on planet Earth. So what is continuum? Read this block here. It says a matter is made up of atoms that are widely spaced in gas phase. Yet it is very convenient to disregard the atomic nature of a substance and view it as a continuous, homogeneous matter with no holes. That is continuum. In other words, guys, we know that if you zoom deep in any matter can it consists of molecules, right? The molecules has an atom and then electrons around it, right? Now there is intermolecular force between the molecules. Now that intermolecular force might be very strong, might be very weak. For gases, it is very weak. And if you remember last week, I said if you are in a room and you spray a perfume at the door, someone at the end of the room will smell it. How come he smelled it? Because it diffuses very fast. The intermolecular forces of gases is very low. Now the issue is if the gas, okay, the gas it consists of atoms. That means if these atoms spread, they will create voids, they will create holes, they will create empty space in between them. Now, in order to deal with any fluid as a fluid, you have to assume there is no void, there is no holes, and that is continuum phenomena. If we don't assume this, we will not be able to analyze any fluid system because our analysis will not be reasonable. We are assuming a bulk of fluid, and yet again, it is not a bulk. Therefore, we always assume continuum phenomena. That is to say, water or a gas is a bulk of a fluid moving together. There is no holes in between them. Okay? 1 second. Right, gentlemen? Okay, so continuum is a very important property, right? This is the case in practically all problems. If you don't assume continuum, you cannot analyze any fluid system. He said in this text, we will limit our consideration to substances that can be modeled as a continuum. That's what I'm trying to repeat here. You have to assume that any fluid moves as a bulk. There is no holes. He is giving, look at this picture. Have you seen a bulk, many birds flying together, gentlemen? You can see them as a fluid, but if you zoom in, you will find voids between them. This is not a continuum. Did you get, guys, the idea of continuum? Shabab,
Yes, Doctor.
did you get the idea? Did you get the idea clearly?
Yes, inshallah.
Yes.
We are still talking about properties. This chapter is about properties. One of the very fundamental, very fundamental property is the density, gentlemen. Density, which is kilogram per meter cube, is a very fundamental property in any fluids, for any fluid and any fluid flow, as a matter of fact. There is a relation between the mass, the volume, and the density, guys. Do you know what it is? The mass is always equal the volume, meter cube, multiplied by the density, kilogram per meter cube. صح ولا ما صح? Am I right?
Yes. الوحدات
Yes.
يروحوا يشيلوا بعض.
Therefore, automatically comes the density is the mass divided by the volume. Right? Specific volume, we said if you divide any property by the mass, you get a specific property. So divide the volume, which is meter cube. Do you see my casa, gentlemen?
Yes, Doctor.
If you divide the volume meter cube by the mass, you get kilogram per meter cube. Meter cube per kilogram, and that is the specific volume. But remember, the density is what? Is meter cube divided by kilogram, صح? No, kilogram by meter cube. So basically, the specific volume is related to the density as what, guys? V equal 1 over rho, or rho equal 1 over V. Remember this relation, guys. This relation is very important. Remember it very careful, underline it. The relation between specific volume and density. Ya shabab.
Yes, Doctor.
Okay, now you agree with me that water is always taken as a reference. صح ولا ما صح? The density of water, we know if you ask anyone what is the density of water, he will tell you 1,000, صح? 1,000 kilogram per meter cube.
صح.
So water is a reference fluid, gentlemen. If you divide the density of any fluid by the density of the water, it gives you something called the specific gravity. Right? SG, specific gravity. So if SG is higher than 1, that means what? Do I have a fluid heavier or lighter than water?
Heavier.
Heavier. If I have SG, specific gravity, less than 1, that means this fluid is lighter than water. So please be careful, because I remember in one of the exams, I put SG equal 0.85, and then they called me to the exam room. And then the student asked me, what is SG? Are you following me here?
Yes, Doctor.
So if it comes in the exam and I said SG equal whatever value, don't go to the examiner and ask him, don't go to the proctor and tell him, please call me Dr. Ibrahim Abdullah, because I don't know SG. It will be very bad. SG is the relative specific gravity, equal rho over rho water. There is a table here that gives you the SG. For example, water is 1 because you are dividing water by water. صح ولا ما صح يا شباب?
صح. نهج القواعد.
Yeah, look at blood, right? Blood is heavier than water. Look at this. What is this? Ethyl alcohol. Ethyl alcohol, 0.79, lighter than water. Look at this. Balsa wood, or I don't know what it is. What is balsa wood? Balsa wood. Look at gold. Look at gold. Gold is gold, gentlemen, huh? You see, gold is very heavy. صح? Where is mercury? Mercury, we always use it. You see mercury, how much? How much is mercury, ya shabab?
13.6.
Very heavy fluid compared to water. Okay? Now, specific weight, if you multiply rho by the gravity, it gives you what, guys? Specific weight.
Specific.
Specific weight. Specific weight equal rho g. Multiply the density by gravity, you get a specific weight. Please pay attention, because in the exam, I might give you one of these properties. If I give you a specific weight, I didn't give you density. Can you get the density?
Yes.
You divide by how much?
9.81.
9.81. Simple as that. Okay. Now, ideal gases, gentlemen. We are still talking about fluids. تفضل.
السلايد اللي قبله اللي هو في السبيسيفيك ويت. الوحدة ليش نيوتن على متر تكعيب مو
why is it Newton, guys, per meter cube?
مو انه الدنسيتي حيكون كيلو جرام على متر كيوب ضرب اللي هو 1 over second square جي.
Right. I think this is dimensional analysis, but let me help you. The density is meter cube per kilogram, صح؟
ايه.
وبعدين
لا density كيلو جرام على
sorry, kilogram per meter cube, sorry. Density is kilogram. I will tell you, I will help you to understand it. Per meter cube. Am I right or wrong?
Yes.
Multiplied by what? G is an acceleration, صح?
Yeah.
Acceleration. Now, let me ask you a question. What is the multiplication of mass by acceleration?
Mass by acceleration, velocity.
Newton.
Come on, man.
لا حسب اسمه. والله ما أعرف.
Someone said force.
Yes.
صح? It is a force, my friend.
Yeah,
If you multiply a mass by acceleration, it is a force. A force unit is what?
Newton.
Did you get it now?
Yeah, yes, doctor. Thank you.
Let us talk to ideal gas. I think you have done this in your preliminary studies. We know that PV is equal RT, صح? For any ideal gas. Gases are two classes. There is real gases and there is ideal gases. We are not going to talk about real gases in this course. We are going to talk about ideal gas. An ideal gas is connected by what? PV equal what? RT. Now, but we can say, we know that, remember, this is a small volume, not capital volume, ya shabab. But if you say PV, capital V, you have to say it equal what? M R T. صح ولا ما صح يا شباب؟
صح دكتور.
You learn this in your, right? Now the mass, do you remember the mass? The mass is equal the number of moles N multiplied by what? The molecular mass. Do you remember, guys?
Yes, doctor.
Right. Now, if you multiply PV over NT, over number of moles NT, C, that will become equal mR. Capital M, that is the molecular mass, multiplied by R. R is the gas constant for any gas. Avogadro hypothesis says mR is constant, or this amount is constant. PV over NT is constant. And mR, M is the molecular mass, and R is the gas constant, which is equal to the universal gas constant R naught. R naught, the universal gas constant, which is equal what, guys? Equal what? 8.139, something like that. 8.314. Here it is. 8.314. So this is the universal gas constant. If you want to get a gas constant, let us say for oxygen, you have to divide 8.314 by what, guys? O2. Assume I want R for O2. How much is the molecular mass for O2? Do you remember, guys?
16.
12
16.
32, صح?
or 16.
32. So you have to divide 8.31 by 32 in order to get the gas constant for O2. Is the idea clear to you? What is the gas constant and universal gas constant? Clear to you this point?
Yes.
Brilliant. Thank you very much. Let us move on. So here he is talking about the gas equation PV equal RT, and other information we are not very much interested in it. This is a simple example which is the relation between mass, density, and volume. He says determine the density, specific gravity, and mass of air in a room whose dimension is 4 by 5 by 6. So he gave you the volume in meter cube. He gave you the pressure as 100 and the temperature as 25. He wants the density. There is an equation, I forgot to mention it to you, which is basically the relation between pressure and P equal rho RT. Do you agree with me? Have you seen this? Where is it coming from, this equation? Where is it coming from, guys?
Now for the volume.
Yeah, the volume is 1 over rho. So that is it.
Yes.
This small volume, we have just been talking about it. V is 1 over rho. So that basically gives you this equation, P equal rho RT. Okay, so here he used the density P equal rho P over RT. Straight away, specific gravity, he divided by 1000 because 1000 is the density for water. He got the density for that gas. He divided to get specific gravity. The mass flow rate is the multiplication of what? Density by the volume. This is a very simple equation, a very simple demonstrative example that basically tell you what is the relation between mass, volume, density, and specific gravity. PV, this is our main equation. PV, if you are not confused, PV, small v, equal RT. Okay, this is the universal, this is the gas equation, this is the ideal gas equation. V is equal 1 over rho. Therefore, P equal rho RT.
Doctor, do we use here PV equal nRT?
Well, you can use, if you use that way, there are many ways to go. If you say PV V equal MRT, you are correct. You are absolutely correct. But can you use this equation?
It depends.
Where will you get the mass? Where will you get the mass from? The mass is required. If the mass is given, you are absolutely right to use it. But the mass is required here. Here, the mass is one of the required items.
What about number of moles, like nRT?
Well, do you have the number of moles?
So it depends on the question. I can understand.
It depends on the given in the question.
Okay, thank you.
It depends on what is given in the question. There are many rules. In physics, generally, guys, there are many rules. But you have to start right. You need to know your starting point. And your starting point is based on what is given. So someone's put this a PV equal MRT. No, what? Okay, I have the pressure, I have the temperature, right? I might even have R. R for gas, for air is given. You can be given R for air, right? And you are given the volume. You can also, by the way, you can still use this one because R is given, T is given, P is given, V is given. You can get M, and then you divide M by the volume to get the density. That is also correct. So look at the given always, but the problem is very simple. You can go either way. You can use this one, you can use this one. This is a simpler way. This is a slightly longer way. Okay? Now, we are still talking about properties, and here we'll talk about vapor pressure. Gentlemen, you remember in your thermodynamic, you have the PV diagram and TV diagram, صح?
Yes.
Huh? And you learn that for every temperature there is a specific pressure called saturation pressure. So saturation temperature, saturation pressure.
From the third.
Right? From thermodynamics, you have learned this, right?
Yes.
PV, TV diagram, and so on. So I think saturation temperature and saturation pressure are not difficult for you to understand. The vapor pressure is basically equal to saturation, because at this point, do you remember, at this point, water starts to boil, right? If we're talking about water. At this point here, all the water has changed to gas. If you continue add heat, we go into the superheat region. صح يا شباب?
Yes. Right.
So this is liquid, this is mixture, this is superheated gas or superheated steam. Now, the partial pressure, guys, that is Dalton law. If you have heard about Dalton law, if you have P over P total, that is the partial pressure. Sometimes, gentlemen, don't get me the partial pressure now. I'm explaining the vapor pressure. Sometimes, although every property, every liquid has this, you can build a TV diagram. That is to say, at this pressure, it needs this amount of temperature in order to start to boil, and so on. Sometimes this condition is violated where, while the temperature remains the same, the pressure drops a little bit. And if the pressure drops, cavitation will take place. Read this bulk here. No, read this here, sorry. Read this point here. It is possible that, he says what? There is a possibility of the fluid pressure in the liquid flow systems dropping below the vapor pressure at some locations, and the resulting unplanned vaporization. You can see there is bubbles. This phenomena, gentlemen, if you stand near the sea, although you cannot watch it very much, but sometimes it happens, right? So basically, if a sudden drop in pressure takes place, vaporization of the water at the surface happens. And this is called what, guys? This is called vaporization, or it causes cavitation. Now, cavitation is a very common problem in pumps. Okay? A pump was supposed to work at a specific pressure in order to push the water at a specific temperature. If the pressure drops below the saturation value, cavitation will take place, and you are losing both power and quantity. Okay, there is an example here. It says what? In a water distribution system, the temperature of water is observed to be what? 30 degrees. Determine the minimum pressure allowed in the system to avoid cavitation. And we have just been talking about the fact that the moment the pressure goes below the what, guys? The saturation pressure, cavitation takes place. And we know for each temperature, there is what, guys? There is a saturation pressure. Do you remember in your thermodynamic, guys? So for example, let us assume that day, assume you are working in Marafiq, okay? Assume you are working in Marafiq, and that day the weather tells you that the temperature is about 30 degrees. That means, gentlemen, the pressure in the pipeline, you have to watch, the pressure in the pipeline should not drop below what, guys? Below what?
4.25.
4.25. If it drops below 4.25, cavitation will take place in the pumps. Cavitation will take place in what? In the pipeline itself. What is the result of cavitation, guys, if it takes place? What are you losing or gaining as an engineer? You want to maximize the amount of water to be pushed to Jebel City. You are just near Jebel University College. You see those barrels, those big barrels behind us?
Yes.
Yes.
So you are sitting there, you have a very powerful pump, and you are pushing water from those barrels or from those tanks into Jebel industrial area. And the temperature is 30. Make no mistake about it. If the pressure in the pipeline drops before 4.25, cavitation will take place. And when cavitation takes place, basically you are pumping water plus air. So the amount of water you are pumping will decrease, right? Am I right or wrong?
Yes, doctor, you're right.
And not only that, cavitation is very harmful to pumps because the pump has to do more work in order to pump a two-phase, because you are dealing with a two-phase, guys. When water and air comes together, this is not a single phase. This is two phases. So you pay attention. So here the problem is, he's telling you, determine the minimum pressure at temperature of 30. At temperature of 30, the pressure is 4.25. Am I right or wrong? Let us go back. Pressure of 30, 4.25, صح?
Yes.
We have been here we are. Right? So you need to have a pressure of 4.25 kilopascal minimum. Don't go below it. If you go below it, you are going to lose a lot. Again, we are still talking about properties, energy and specific gas and specific heats, right? How many forms of energy, guys? There are many forms of energy. There is internal energy, there is kinetic energy, there is potential energy, and I'm going to stop in this slide. That is slide 15, and I will continue from here on Thursday, inshallah. I want to see if you have 5 minutes for questioning, guys.
Doctor, do we stop here?
Yeah, we're going to stop here now. You have 5 minutes to ask me any questions before we leave.
Okay, Doctor, I have a question.
تفضل.
كيف طريقة المذاكرة بتكون في هذه المادة؟ أنا أحب أعرف.
So why are you changing from English to Arabic? Let us stop